Welcome back for another deep dive. We always think of Einstein and relativity, but today we're going to explore a different side of him, his relationship with quantum physics.
Yeah, it's fascinating, really. Most people don't realize how central his work on light and energy was to the whole field of quantum mechanics.
Absolutely. And to dig into this, we're going to be looking closely at an essay by Yuriko Schneeppert called Albert Einstein, Wegbereiter der Quantentechnologie, which translates to Albert Einstein, pioneer of quantum technology.
Great essay. Schneeppert does a fantastic job.
He really does. And by the end of this deep dive, well, I'm hoping you'll not only understand Einstein's role in the birth of quantum mechanics, but you'll grasp some of the core concepts of this revolutionary field, too.
I think so, and maybe even challenge a few assumptions about Einstein along the way.
Oh, definitely. One thing that really jumped out at me reading Schneeppert was how Einstein was working a day job at the patent office while making these huge GE discoveries. It's kind of inspiring in a way.
Yeah.
Like, what amazing ideas are we all overlooking in our daily routines, right?
It's a great point. It really highlights Einstein's dedication and natural curiosity. And, well, to really understand the impact of his work, we have to remember the context. Back then, a lot of physicists believed they'd already figured out the major laws of the universe.
Right, like physics was nearly complete.
Exactly. But then Einstein comes along, and his work on things like Brownian motion, that seemingly random movement of particles suspended in a fluid well, it starts to challenge those assumptions.
Ah, so he was already shaking things up even before quantum mechanics.
Exactly. And then, boom, comes his 1905 paper on the photoelectric effect, which, as Schneeppert details, introduces this radical idea. Light can act like a particle, a photon.
Hold on, a particle. Like, I always thought of light as a wave.
Right. It's hard to imagine now, but back then that concept was totally revolutionary.
So it's like saying a beam of light isn't this continuous wave, but more like a stream of tiny bullets of energy.
Exactly. And the photoelectric effect provided the evidence. Basically, when light hits a metal surface, it can knock electrons loose. But, and here's the weird part, the energy of those electrons doesn't depend on the brightness of the light like you'd expect if light was just a wave.
So what does it depend on then?
The color or frequency of the light.
So blue light, for example, would have a different effect than red light.
Exactly. And Einstein explained this by saying that light is made up of these discrete packets of energy, these photons. Each photon carries a specific amount of energy determined by its frequency. And this is where his famous equation, EAF, comes in.
Okay, stop right there. I got to ask about that equation. It feels like the key to this whole thing. Can you unpack it a bit?
Sure. So E stands for the energy of a photon. H is Planck's constant, which is this tiny fundamental number in physics. And F represents the frequency of the light.
Okay, so far so good.
So what the equation tells us is that the higher the frequency of light, the more energy each photon carries. That's why ultraviolet light, which has a higher frequency than visible light, can give you a sunburn, while infrared light, which has a lower frequency, mainly just provides warmth.
Okay, that makes sense. So if I'm getting this right, Einstein showed that light can act as both a wave and a particle. And the energy of those particles, those photons, is directly related to the light's frequency. Mind-blowing stuff.
It was truly groundbreaking. But here's where the story gets even more interesting. Schneeppert points out that while Einstein's work on the photoelectric effect really solidified this whole idea of energy quanta, these little packets of energy, it actually built upon earlier work by Max Planck.
Right, Planck's quantum hypothesis. I've heard of it, but I'll admit I don't fully understand it.
Well, Planck kind of stumbled upon the idea of these energy quantas a few years before Einstein. But what's fascinating is that Planck himself wasn't entirely convinced by the implications of his own theory. He saw it more as a mathematical trick than an actual description of reality. It was Einstein who really ran with the idea and showed that energy is fundamentally quantized, meaning it comes in these discrete packets, not continuously.
Ah, so it's a great example of how scientific progress builds on itself. Right. One scientist's mathematical trick becomes another's revolutionary breakthrough.
Absolutely. And, it happens all the time in science collaboration and building on each other's work. Really amazing things can come from that.
Yeah, I guess even when scientists disagree, there's still this kind of collaboration happening. Because, well, as I'm sure you're about to tell me, Einstein, despite being one of the, four fathers of quantum theory, ultimately became one of its biggest critics.
You read my mind. It's true. As Schneeppert points out, Einstein was deeply uncomfortable with the direction quantum mechanics was taking. You see, at its core, quantum mechanics is probabilistic, It says we can only predict the probability of a particle being in a certain state, not its definite state.
Mm-hmm.
And this uncertainty, the idea that randomness is inherent in the universe, it really bothered Einstein. I mean, he famously said, God does not play dice. He believed in a universe that ran on order and predictability.
So it wasn't that he thought quantum mechanics was wrong, exactly. It was more that he felt it was incomplete, that there was a deeper level of reality we weren't grasping.
Precisely. He believed there must be some underlying mechanism, some hidden variables that determine the definite state of a particle, even if we couldn't observe those variables directly.
Fascinating. So this is what led him to the EPR paradox, right?
Exactly. Einstein, Podolsky, and Rosen, as Schneeppert explains, they devised this thought experiment to try and expose what they saw as flaws in quantum mechanics.
Okay, so the EPR paradox, what exactly did they propose?
Well, it focused on one of the most bizarre and frankly counterintuitive aspects of quantum mechanics, entanglement.
Entanglement. Okay. Now this is where quantum mechanics starts to sound like science fiction. Tell me more.
All right, so imagine two particles that are linked or entangled in such a way that their properties are correlated even when they're separated by vast distances. If you measure a property of one particle, like its spin, you instantly know the corresponding property of the other particle no matter how far apart they are.
Wait, so that's what Einstein called spooky action at a distance.
Exactly. And it's precisely what troubled him so much. He just couldn't accept that measuring one particle could instantly influence another one across vast distances. It just didn't fit with his view of a universe where cause and effect operate locally. He believed there had to be a simpler explanation, and that's where the idea of hidden variables came in.
So he was saying that the particles already possessed those correlated properties before we even measured them. We just weren't aware of those hidden variables that predetermined their states.
That's the gist of it. He refused to believe that the act of measurement itself was creating this connection. It was a fundamental clash of worldviews.
This is fascinating. So did Einstein ever succeed in finding his hidden variables and disproving this spooky action at a distance? I'm on the edge of my seat.
Well, not really, no. Einstein's quest to find those hidden variables is kind of a story in itself. It remained a theoretical debate for decades. There just wasn't any way to experimentally prove or disprove these hidden variables.
So how did physicists even move forward? I mean, it sounds like they hit a wall.
You're right, it did seem like an impasse. But then, in the 1960s, a physicist named John Bell came up with this, brilliant way to test the whole hidden variables idea. It's known as Bell's theorem, and it had a massive impact, really, on how we understand quantum mechanics.
Bell's theorem. Okay, this sounds like a turning point in our story here. What exactly is it?
Well, Bell's theorem basically gives us a way to distinguish between the predictions of quantum mechanics and any theory that's based on these local hidden variables. You could say it set up a kind of showdown.
So a way to put Einstein's skepticism to the test.
You got it. Bell basically showed that if there were these hidden variables influencing the properties of entangled particles, the results of certain experiments would have to fall within specific limits. These limits are described by mathematical inequalities, what we now call Bell's inequalities.
Okay, I'm following so far. So if the experiments ended up violating Bell's inequalities, then that would mean hidden variables were out, and quantum mechanics, with its spooky entanglement, would be the winner.
Precisely. And those experiments started happening in the 1970s and 80s. Physicists like Elaine Aspect, they conducted these groundbreaking experiments that really tested Bell's inequalities, like with increasing precision.
And drum roll, please.
Yeah.
What were the results? Was Einstein proven right or wrong?
Well, the results were pretty conclusive, I'd say. The experiments violated Bell's inequalities, and that, of course, supports the predictions of quantum mechanics. It was a significant blow to that whole idea of local hidden variables.
Wow, so it seems like Einstein's quest for a deterministic universe, at least in this case, didn't work out. But I imagine his, skepticism still had an impact on the field, right?
Oh, absolutely. Even though Einstein was wrong about those hidden variables, his persistent questioning and challenges to the foundations of quantum mechanics were incredibly valuable.
It's funny how being wrong can actually move science forward. How did that happen in this case?
Well, think about it this way. Einstein's constant search for a deeper explanation pushed other physicists to really scrutinize quantum mechanics, to look at its foundations really closely. His challenges forced them to, refine their experiments, clarify how they were interpreting things, and it ultimately deepened our understanding of these really strange quantum phenomena.
So he was kind of like a worthy adversary, pushing the field forward even while resisting some of its core principles.
Exactly. And here's another layer of irony. Even though Einstein found this whole entanglement thing so troubling, His work, in a way, paved the way for some of the most groundbreaking technologies we see today.
Wait, really? His work led to things he fundamentally disagreed with.
It did. It really shows the unpredictable nature of scientific progress. You just never know where a line of inquiry, even one that seems like a dead end, will end up leading. And going back to Schneppat's essay, he emphasizes how Einstein's legacy in quantum physics goes way beyond any specific right or wrong answer. He really sparked a debate about the nature of reality, and it's a debate that's still going on today.
Yeah, it does seem like a very philosophical debate, just as much as a scientific one.
It is. It gets to the heart of some big questions, like, what is reality? Is the universe fundamentally random, like quantum mechanics suggests, or is there some deeper level of order and determinism that we haven't figured out yet?
Those are questions humans have always asked, but quantum mechanics really brings them to the forefront. If we can only predict probabilities, does that mean there's no objective reality until we measure something?
That's really the key point. The Copenhagen interpretation, which is the most widely accepted interpretation of quantum mechanics, and one that Einstein, famously opposed, suggests that it's the act of measurement itself that influences the state of the system. Before you measure something, a particle exists in this superposition of states, and it's only when we observe it that it collapses into a definite state.
That is so counterintuitive. Like it's saying the universe doesn't make up its mind until we look at it. It's hard to even imagine that.
It is a mind-bending concept, that's for sure. And even today, there are physicists who just aren't comfortable with this idea and are searching for other interpretations that might bring back a more classical, objective reality.
So what Schneppat seems to be saying is that Einstein's legacy, his impact on quantum physics, goes way beyond any specific contribution or being right or wrong.
Mm-hmm.
He helped start this debate about the very nature of reality, a debate that is still going on today. He was a real pioneer, even in his skepticism.
He was. And what's so interesting about all of this is that we still don't have all the answers. There are still mysteries to solve in the quantum realm.
That's what's so exciting about science, right? It's not about dogma or finding the one right answer. It's about constantly questioning, exploring, and pushing the boundaries of what we know. And that's exactly what Einstein did throughout his career.
You said it. He challenged the status quo even when it made him unpopular, and in doing so, he really shaped the future of physics. His pursuit of truth, even when it led him down unconventional paths, continues to inspire scientists today.
Well said. This has been a fascinating look at Einstein's relationship with quantum physics. I feel like I have a much better understanding of both science and the man himself.
It's been great exploring these ideas with you. And for you, our listeners, we hope this deep dive has given you a glimpse into this fascinating world of quantum physics and the enduring legacy of Einstein.
Einstein showed us that even when you're wrong, asking the right questions can lead to incredible discoveries and really push the boundaries of human knowledge. So keep exploring, keep questioning, and never stop diving deep into these mysteries of the universe.
And with that, we'll leave you with this final thought. Einstein never fully accepted the probabilistic nature of quantum mechanics. Does that mean there are still deeper layers of reality out there, just waiting to be discovered? Perhaps a theory that can bring together these seemingly contradictory worlds of the very large and the very small. The quest, you could say, continues.
It's amazing to think this whole debate started by Einstein is still going strong all these years later. I wonder what he would think of all the advancements in quantum physics today.
Yeah, me too. It's interesting that Schneppat's essay doesn't talk too much about modern quantum technology, but I think Einstein would be both fascinated and troubled by it, you know what I mean?
Yeah, I see that. His work was so essential, but at the same time, he was never comfortable with the whole thing.
Right, and it really shows how important it is to challenge assumptions, even the ones we really want to believe. Einstein's insistence on a deterministic universe, even when the evidence pointed in another direction, really pushed the field in ways he probably never imagined.
It's a good reminder that science isn't about finding the answer. It's a process, a journey. There's always something more to learn, to question. And often, the answers we find lead to even bigger questions.
That's a great way to put it. I think Einstein, with his constant curiosity and willingness to challenge the status quo, would agree with you there. He was a true pioneer, not just in his scientific discoveries, but in his commitment to finding the truth, no matter where it led.
So as we wrap up this deep dive into Einstein's quantum legacy, what's the one thing you hope our listeners take away from all of this?
I think the most important thing to remember is that Einstein's story is not just about physics. It's about critical thinking, challenging what we think we know, and that constant human desire to understand the universe and our place in it.
Well said. And who knows, maybe someone listening right now, inspired by Einstein, will make the next big discovery in quantum physics.
I wouldn't be surprised at all. After all, as Einstein once said, the important thing is not to stop questioning. Curiosity has its own reason for existing.
That's a great quote. And on that note, we'll leave you to ponder those mysteries of the quantum world. Until next time, keep exploring, keep questioning, and keep diving deep.